All right. Fundamental theorem of calculus. The fundamental theorem of calculus is actually split into two parts, and we are going to talk about both parts today. The first part is this, and it's kind of complex to look at to begin with, but we'll break it down, and it's actually a very kind of simple idea. It says this: if f, which is this function right here, is continuous on the interval from a to b, then the function capital F of the integral from a to x of f of t dt has a derivative at every point x on the interval from a to b. And the derivative of that capital F is the derivative of the integral, which will end up being the function inside the integral evaluated at x. Say that question again. Of the function inside the integral. Yep. Before we move on to use this, I'm going to flip to the next page, and it kind of simplifies this. What is this fundamental theorem of calculus part 1 doing? Well, it's saying that the derivative of this integral is the function that is inside the integral. And I'm going to pause right there. It says, first of all, a couple things that have to be true for us to be able to actually apply this. The lower limit would be some constant, some number. The upper limit is some x. And I have x in quotation marks because for a minute we're going to see it as x, and then we're going to see what happens when it becomes some function of x and how we then follow our rules for this. Before we move on to actually doing an example, I want to take a second and read to you what your book says about that fundamental theorem of calculus part 1. So looking at that top equation, this is what your book says, and I just really like the words that they used. And they said it's difficult to overestimate the power of that equation. It says that every continuous function is the derivative of some other function, namely that is that one right there. It says that every continuous function has an antiderivative. And it says that the process of integration and differentiation are inverses of one another. If any equation deserves to be called the fundamental theorem of calculus, it's this one for sure. So we see that the derivative and integration are opposites of each other, that every continuous function is integratable, and every continuous function has an antiderivative. So applying that, a very basic application of what we see up there. If we see that the bottom bound is some number of our integral, and we're doing the derivative of this integral, right? That's what we're taking the derivative of. That our answer will be the function inside evaluated at that function of x, which in this case is just x, at the top of our integral. So our answer, the derivative of this, is the cosine of x. Again, that we're seeing that the derivative and the integral are inverses of each other, giving us just the function inside. Now, because they chose to use the variable x as the upper number in our integral, that's why you see them do the function inside in terms of t, so that we don't get confused with a ton of x's just showing up everywhere. So again, same thing here. Remember that 0 is a number. We've got that x up there, so the derivative of this integral is the function inside evaluated at x. So the derivative of this integral would be 1 over 1 plus x. Questions so far? Okay. So adding a few things to this concept, what if that function at the top is not just a plain x, but some sort of function of x, like we have in this one, x squared? Okay. Well, when we do this, it becomes a chain rule. The derivative of the integral still just gives us the function inside, cosine x squared, whatever's in the top here. So it's going to look like you are, again, evaluating that inner function at x squared. But then it's chain rule. So now derivative of the inside function. So derivative of x squared, which would be 2x. So when we have that function at the top of our integral not being just a plain x, you have to still plug it in. But now then follow it up with the derivative of that function as well, times the derivative of that upper bound. Okay. What if we have that reversed, and we've seen this before, where it's not a number up to x, but x is the lower bound and the number is the upper bound? What did we do to switch the bounds? Negative, right? So instead, I can say that this equals negative, switch the bounds, negative 5 up to x. And then proceed like normal. Well, taking the derivative of something with a constant multiplier of negative 1 out front just takes our answer and multiplies it by the constant multiplier of negative 1. So our answer here would be negative, plug that x in, 3x. Questions? All right, so take a second and try a couple of these. Give you a minute to work ahead of me. All right, applying that fundamental theorem of calculus, we are taking the derivative of an integral. And again, those are, we just learned are inverses of each other, that this is a chain rule here. I'm going to take that 3x squared and start by plugging it into the function. So our derivative equals 5 times the secant of 3x squared times the derivative of what I plugged in. The derivative of 3x squared would be 6x. Probably could clean this up. 30x secant 3x squared. Second one, again, remember that we are just getting the function inside the integral when we take the derivative evaluated at that top bound. So as I do that, I'm going to take the 2x squared, and it goes into that function where it says t. So it'd be 2 raised to the 2x squared times the derivative of what we plugged in. The derivative of 2x squared would be 4x. And there is nothing you can do to simplify that one. You can't like take the 2 times a 4 or anything. So that would be as far as we can go, really. Questions? Last one, again, I would look at what's inside of here. I need to switch my bounds because the number's on the top, and to do that, we would make it negative. And now I can apply my fundamental theorem of calculus and plug the 5x in. And that's more than just a plain x, so then I would follow this up by multiplying by the derivative of 5x, which is 5. Simplify, we'd end up with negative 5 over 1 plus 25x squared. Questions so far? Would anyone still like this page? All right. How can we use this idea to create a function with the given derivative? So constructing a function, y equals f of x, that has the derivative of dy dx equals tangent of x. We know that if we take the derivative of an integral that goes from a number up to x of a function, that we just get the function inside evaluated at x, right? So that's kind of the idea of what we're doing here. But I need to then also include the given condition that f of 3 equals 5, okay? So remember what we're looking at here. F of 3 would be an x value. And I'm going to bring back into play one of our integral properties to help us with this. If I look at doing the integral from that x value, 3, of tangent of t dt, and let's say I were asking you to evaluate this at 3. If I plug that in for x, and we evaluate an integral from 3 to 3, what does this end up equaling? If I evaluate an integral from a number to itself? 0, right? So this much right now of this function when I evaluate it at 3 is 0. But I need f of 3 to equal 5. So right now, I've created it so that this is equal to 0, so it's easy to make this equal 5. What would I need to add on? 5, right? Now, how did I do that? Well, I picked the x value that they asked me to, or that they gave me the information about, f of 3. And that's where I chose to start my integral, because remember, to use our fundamental theorem of calculus, it has to go from a number up to x. Well, I picked the number down here based on the given information, because then I know that this will be 0 at that particular x value. So to make this part true, I can just add on whatever it equaled. Questions? See how I did that? See where the numbers went? So we create the integral. This becomes the function inside my integral. This becomes the lower bound. This is what gets added on. Try it on your own. Create a function, f of x, that satisfies the given conditions. The derivative of your function is going to equal cotangent of x secant cubed of x. And f of 75 equals 144. right, so using our calculus to create this function that has this as a derivative and this is a value at x equals 75, my function is going to be the integral, and again, I'm going to start my integral at the x value they gave me. So the integral from 75 to x of the function that is supposed to be my derivative. So the cotangent of t, secant cubed of t dt. Because now as I evaluate this at 75, this part of it's going to go to 0 because it'll go the integral from 75 to 75. So then I will add on whatever is supposed to equal 144. And this function then now satisfies both of the given conditions. If I were to take the derivative of this, first of all, the derivative of the integral is going to give me the inside function. The derivative of a constant, gone, right? And evaluating that at 75 will equal 144. Questions for me? Okay, part 2. Now, part 2 should look familiar. We have done part 2. If f is continuous at every point on the integral from a to b, and if the antiderivative is f of f on a to b, then we know that we can evaluate the integral from a to b of f of x dx by doing the antiderivative of b minus the antiderivative of a. We did this already. We just kind of referred to it as evaluating an integral analytically. Well, it has a title, Fundamental Theorem of Calculus, Part 2. Couple different ways we can go about showing this. We could show it exactly like we were showing it in our notes previously, identifying for ourselves the antiderivative. This one, in the example given, our function is x cubed plus 1, so it looks like we're thinking backwards through our power rule, right? If we had landed at an x cubed, that would have come from an x to the 4th. Two different ways you can think about this. 4 times some number gives me 1, or work your way backwards. 1 divided by our new exponent is what would be in front of here, so we should have a 1/4 x to the 4. And then what's the antiderivative of 1? X. Okay. You can show it by saying that you are evaluating this from -1 to 3. You can show it this way if you like that notation. You could show it the notation we were doing previously, capital F of, oops, 3, not -3, 3 minus capital F of -1. I don't really care, but either way, we plug in 3, get a value, minus, plug in -1, get a value, put it all together. You guys will have to check my math on this. 3 to the 4th is 81. So we get 93/4. That'd be 1 minus 1. 96/4. Which is what, 24? Did I do okay with my mental math up there? It's always suspect. Any questions on this? Antiderivatives should look familiar. We've done that, right? So the last part is this. As we look at this last problem, I would say that especially because of the mode we are in right now, in this whole world of integrals, etc., that we would read this too quickly, that we would kind of not slow down and think about what we're doing and set this up incorrectly based off of one little phrase that's in the directions. It says find the total area between the curve y equals 4 minus x squared and the x-axis on the interval from 0 to 3. Now, immediately my mind went to, ooh, area under a curve. That's the integral, right? Agreed? Area under a curve is the integral. So I was like, okay, well, I'll just set up the integral from 0 to 3 of that function, 4 minus x squared dx, right? And it's going to find me the area under that curve. Which, who's got a calculator? What is that answer? Math 9 that. It is. Okay. Now, I kind of told you that that was not going to be right. Does anyone know why? Yeah, that little phrase up there that says total area doesn't want you to talk about whether something is negative or positive, but an integral does that, doesn't it? It adds positive areas, but it subtracts negative areas to get a, like first semester, you remember the conversations we had a lot first semester about displacement versus total distance traveled? Okay, kind of the same idea. Our integral is our displacement, and our total distance traveled is our total area, where we don't take into account that it's positive, negative. We're just adding areas together, right? So to do that, this is wrong because it included taking out negative areas. And we don't want to take out areas. We just want to say what's shaded. Okay, it doesn't matter where it's at, what's shaded. So to do that, we're going to have to break up our picture by positive and negative areas. Okay, and in order to do that, now this one's a pretty easy one to do that, but in order to do that, we would have to find the zeros of our function on that integral so that we know where to make those breaks, right? And ours is pretty easy. So to do that, we're going to find our zeros. Right? Ours is exactly, we can set our function equal to 0, but it's 3, isn't it? So we have positive area in this part. Now, to find that area under the curve, can't I just do an integral from 0 to 2? Yes, that is true. I can do that. So I can do the integral from 0 to 2. This represents all the area in our picture that is above our x-axis. Okay? And again, somebody math 9 that for me. The area that's below our x-axis would go from 2 to 3. But if I do this, what kind of an answer am I going to get? If I do the integral from 2 to 3, what kind of answer is that going to be? Negative. So I don't want that. I can do one of two things. I can either subtract this knowing that it's going to be negative, or just absolute value it, right? We're just totaling up these areas. Okay, so what was our area from 0 to 2? Who math 9 that for me? Okay, and how about that second area? Negative 2 1/3. Okay. Putting that one into absolute values, add those together, it looks like we get, what, 7 2/3? Or 7.667. Okay. And then can you see that if I put those two parts together, that's why we got an answer of 3 up here? Okay, because if I were to actually have taken that as the negative 2 1/3, it would have been a total of 3 together. So look for those directions. Do you see how easy it would be to just do the integral from 0 to 3 if I didn't really slow down and think about what they were asking me? Okay, because I see area under a curve and I think integral. When it's asking for total area, they're not wanting you to say that this is negative. They're just saying find us all the shaded stuff and put it together. Okay? Any questions for me?